Hi everyone. Today I'm going to go through patterns and sequences in series. Okay, so first of all, you have linear sequence, quadratic sequences, cubic sequences, and geometric. So I want to start off with a linear sequence. So a linear sequence is something that will go like this. So say 2, 4, 6, 8, 10. Basically, how you can tell it's linear is how do you go from the first to the second? You add 2. How do you go from the second to the third? You add 2. How do you go to the next one? You add 2, and then you add 2. Okay? So that's what makes it linear. The fact that you just add 2 every time. Okay? Another linear sequence would be something like 3, 1. I might do a different thing. 3, 2, 1, 0, -1, -2, and so on. Because how do I go from this one? I just -1, I'm -1, I'm -1, I'm -1, and I'm -1. Okay. So that's how you identify a linear sequence. This is called the common difference D. So these things here, you would call D. So in this case, the first one, the common difference is 2. In the second case, the common difference is -1. Okay? So that's all. So now, that's how you identify a linear sequence. Now, the next thing that they'll ask you is they'll say, okay, this is called T1 because it's the first term. This is called T2 because it's the second term. This is T3, the third term. This is T4, the fourth term. And this is T5, the fifth term. Now, if I asked you what the sixth term was, T6, you would say 12. Why? Because you just add 2 to T5 and then you get T6, which is 12. We want a way to figure out what Tn is. So this is the nth term. So on top we have the first, second, third, fourth, fifth, sixth. But what if I wanted the 1,000 term? How would you figure that out? Is there a formula you can use? And the answer is yes. There is a formula you can use for linear sequences. So Tn is A plus n minus 1 times D. So in this case, n is a variable. So n is what you plug in. So n is like, if you want the 10th one, you plug in n equals 10. If you want the first one, you plug in 1. If you plug in, if you want the 130th, then you plug in 130 and so on and so on. So now, D is the common difference. And A is simply the first term. Okay? So, if I give you this sequence, say 5, 8, 11, 14, we go up in 3 every time. So this means that D equals 3. And A equals 5. Why? Because it's the first term. Okay? So now if I asked you to solve for Tn, Tn is equal to A, which is 5, plus n minus 1 times D, which is 3. This is equal to 5 plus 3n minus 3. So Tn is equal to 3n plus 2. Okay? So now if I ask you what's the... So just to, confirm that that's what it is. If I solve for T1, T1 is equal to 3 times 1 plus 2, which is 5. So see the way this 5 and this 5. T2, that's equal to 3 times 2 plus 2. That's 6 plus 2, which is 8. So the 8 corresponds to the 8, and so on and so on. So just for example, we've now found the nth term of the sequence, okay? And that's what questions will ask you. They'll ask you what is the nth term. Here, n is an element of n. So n is 1, 2, 3, 4, 5, 6, 7. So there's no such thing as the minus second term. There's no such thing as the 4.5th term. So it's the first, second, third, fourth, fifth, and so on and so on. So if they ask you what is the 100th term, you would just simply do t100 is equal to 3 times 100 plus 2, that's 300, plus 2, that's 302. So the 100th term in this sequence is simply 302. Okay? So hopefully that's all okay. Sorry. Now you also have Sn. So again, sorry, this is called an arithmetic sequence as well. Okay? So linear, arithmetic, it just means that it's linear, like this. Okay? So now they can also ask you for the sum of them. And they say, okay, well, what if you add up the first 100? So the 100th term is 302, but what if you add up the first 100 of them? What's that equal to? The way you do this is there's a formula, Sn, which is if you add up the first n of them, you get n over 2, 2a plus n minus 1 times d. Again, these formulas are in your log table, so you won't have to learn them off. Okay, so if I asked you to, what is the sum of the first 50 in our sequence up here, you would say, okay, well, that's S50, which is equal to 50 over 2 times 2a. So a is 5. So 2 times 5 is 10. Plus n minus 1, that's 50 minus 1, times d, which is 3. That's equal to 25 times 10 plus 50 minus 1 is 49, times 3 is 147. That's 25 times 157. And then that's whatever it equals. Okay, so I can probably do that. So 3, 9, 2, 5, 0, I think. That might be wrong, but you know, something along the lines of that. Okay? No, that's definitely wrong. It's 3050. Sorry, I got my decimal places wrong. Sorry, what did I say it was again? Divided by 4, 3, 9, 2, 5. Like that. So that is what I think that adds up to, but you just plug that into your calculator, see what you get. Okay, I don't have my calculator with me, but that's what I think you would get. Okay, so that's how you if they ask you to add up the first 50 of them, you would get this. Okay, so not too bad at all. They can also ask you, what is Sn minus Sn minus 1? Sorry, I might just write that a little bit lower. So what is Sn minus Sn minus 1? Again, you can pause the video to think. This is equal to Tn. Why? Because Sn is Tn plus Tn minus 1 plus Tn minus 2 dot 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 T2 plus T1. And then you're minusing Sn minus 1, which is Tn minus 1 plus Tn minus 2 T2 T1. So basically all of these terms will cancel except Tn. So that might be a thing that they'll say, okay, so if I wanted to add, so let's say we have the sequence 1, 2, 3, 4, 5, 6. And they ask you, what is the sum of the 21st to the 30th numbers? So they only want the 21st to the 30th. How would you do that? That's equal to S30, so the sum of the first 30 minus the sum of the first 20. Hopefully that makes sense. So in the same way that Sn minus 1 is equal to Tn, S30 minus S20, that's equal to T21 plus T22, T33. Just 30, sorry. Like that. So this is what it equals. So again, first of all, I want to know what A is equal to 1 and D is also equal to 1. Just for the simple fact that the first number is 1 and your common difference is also 1. So Sn is n over 2 into 2 times A, which is 2 times 1, so 2, plus n minus 1 times 1, which is just n minus 1. So Sn in this case is just going to be n over 2 into n plus 1. That's equal to n squared plus n all over 2. So S of 30, that's going to be 30 squared plus 30 divided by 2. So that's going to be 930 divided by 2. That's going to be 465. And then S20, that's going to be 400 plus 20, so 420 divided by 2. That's going to be 210. And therefore S30 minus S20, that's equal to 465 minus 210. That's equal to 255. Okay, so hopefully that's all okay. So that's about the hardest that you can be asked, really. Asking you for the sum of the first 21st to the 30th inclusive. That's the hardest part. Okay. So now, the very next thing is quadratic sequences. So a sequence is quadratic if the second difference is the same. Okay? So let's say we had 2, 5, 10, 17. Now, this is not linear because if we check and say, okay, what's happening? So first of all, I add 3, then I add 5, then I add 7. So now, 3 plus 5 plus 7, they're not the same thing. But if you look at the second difference, now this is a constant. Okay, so just to make a point of it, the first thing is quadratic, then you get something that's linear, and then you get a constant. Okay, so when you get the difference in a quadratic sequence, you actually just end up with a linear sequence. If you get the difference in a linear sequence, you end up getting a constant, and so on and so on. Okay, which is quite interesting. That you just reduce power like this. Okay. So a quadratic sequence, so in the same way that for a linear sequence, you have that it's going to be your Tn is equal to something linear. So remember up here where we found Tn. Yeah, so see the way for a linear sequence, Tn is a linear function. So there's no n squares, there's no n cubes, it's just the highest power is n. So it's linear. The same thing is going to happen for quadratics. So quadratics, Tn is going to be some an squared plus bn plus c. Now, this is, you don't have to know this, but your life just becomes so much easier if you do. The second difference here, that's equal to 2 times a. So in this case, a equals 1. Okay? So to figure out Tn, I have that Tn is going to be n squared plus bn plus c. Now you might be sitting there and saying, okay, well, that's grand. So we figure out A. How do we figure out B and C? Very simple. T1 is equal to what? 2. So if I plug 1 into this formula, I have to get 2. So plug in 1, I get 1 plus B plus c. Grand. If I plug in 2, I have to get 5. So plug in 2, I get 4 plus 2b plus c. Now what I can do is I can minus the equations from each other. So 2 minus 5 is minus 3. 1 minus 4 is minus 3. B minus 2b is minus b. And then c minus c is 0. So I get that b equals 0. Okay? Plug that back into the top equation. I get 2 equals 1 plus 0 is just 1 plus c. So c just turns out to be 1. Like that. So this sequence, Tn, is just going to be n squared plus 1. Okay? So that's that. So that's all you need to do for that one. Okay? That's as much as you can be asked. So there's no summation for this one because it's just too difficult. Okay. So now, for the next one, it's going to be geometric. So geometric is basically when your sequence, so I'll give this its own section because this is the most common. And I will rely on it on the next section to prove one of the answers, one of the formulas. So geometric is basically when your Tn, T1 is equal to A, T2 is equal to A times R, T3 is equal to A R squared, T4 is equal to A R cubed, and Tn is equal to A R to the n minus 1. Okay, so basically a geometric sequence is you start with a number and then you multiply it by a different number and you just keep going. Okay, so how do you go from this one to this one? You multiply by r. You multiply by r, you multiply by r, on and on. So geometric is just when you multiply by r. Okay, so a geometric series could be something like this. 5, 10, 20. So again, here A is the first number. Okay, so in this case, Tn is 5 times 2 to the n minus 1. Why? Because I multiply by 2 every time. Okay, so that's it. Also, Sn, again, you this is in the log tables, you don't have to know how to prove it or anything. It's just A into 1 minus r to the n all over 1 minus r. So again, if they ask you what is Sn, Sn is simply equal to 5 into 1 minus 2 to the n all over 1 minus 2. That's equal to 5 into 1 minus 2 to the n all over minus 1. So Sn is simply equal to 5 into 2 to the n minus 1. Like that. Okay? So the sum of the first n things is simply equal to this. Alright? So again, n is an element of n here. And then that's it. So if they ask you, calculate 5 plus 10 plus 20 all the way up to 2, 5, 60, how would you calculate this? Well, we have a summation formula up here. That's perfectly fine. So how do we figure it out? You just have to sit there and say, okay, well, I have a summation formula. What do I need to plug in? I need to plug in n. I need to know how many of them I want to add up. So this is the first one, grand. That's the second. That's the third. But I don't know what one this is. So what you do is you figure it out. You say 5, 2 to the n minus 1 is equal to 2, 5, 60. divide both sides by 5, I get 2 to the n minus 1 is equal to 512. Now, this is where you would use logs. It is the easiest, this is why logs were mainly invented, for problems like this, where you don't know how to solve this. You can just take log to the base 2 on both sides. Why? Because on the left hand side, we will just get n minus 1. So remember, that's the reason you take log to the base 2. And then when you do that, you know that you'll get n minus 1 coming down out of it. Log to the base 2 of 512, that's 9. So in this case, n just equals 10. So this is the 10th one. So what do I want to do? I want to add up the first 10 of them. So S10, that's equal to 5 into 2 to the power of 10 minus 1. That's equal to 5, 2 to the power of 10, that's 1024, minus 1, 1023. Multiply it by 5, that's 5115. So that's the sum of this to this. So this is equal to 5115. Okay? So hopefully that's all okay. Now, the next thing I want to go over is limits and convergence and divergence. I think these are quite nice, to be honest. And then I'll do the infinite series. So, first of all, limits. What is a limit? So, an example of a limit is you would just say the limit as n goes to infinity of 1 over n. What does this equal? So what do I mean when I say this? I mean, as n gets really, really big, what does 1 over n start to look like? And you can do this, you can plug this into your calculator. You can plug in 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, 1 over 1,000,000,000, and keep going. And what does your answer start to go towards? So what does it what number does it approach? The answer is 0. So the bigger n gets, the smaller the number you get, and the closer it gets to 0. So the answer is the limit as n goes to infinity, you would simply get 0. This is very important. When I say limit, I'm not saying n is infinity. I'm not saying that. I'm just saying as n gets really, really, really big, what does it start to look like? It starts to look like 0. Okay? So just to be clear on that. This is the main one you'll need to know, just to have in your back pocket. It's quite nice to have. So if I started to do the limit as n goes to infinity of 3n minus 1 over n plus 2, what happens here? The very first thing you do is you identify the highest power of n. What's the highest power of n you see here? N to the power of 1. You divide by that power on the top and the bottom. So you get the limit as n goes to infinity of 3 minus 1 over n all over 1 plus 2 over n. Now, you apply the limit as n goes to infinity. You know that 1 over n goes to 0, so this 1 over n will also go to 0. And this 2 over n will also go to 0. Why? Because if n gets really, 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 really big, then 2 over n is roughly 0. You're just saying it's roughly 0, or it goes to 0. You're not saying it is 0, you're saying it gets really small after a while, and it's like rounding. You just say, listen, it's too small, don't care about it, let it be 0. And so you're left with 3. And you can do this. If you plug in 1,000 or 1,000,000 or 1,000,000,000, you won't exactly get 3. You'll get something that's very, like, slightly smaller than 3, but it will eventually you'll get 2.9, 2.99, 2.9999, 2.79s after it, and then you'll say, okay, yeah, that's approaching 3. So you can imagine that as n gets stupidly big, you start to get loads of loads of 9s, and you say, okay, yeah, just round that, it's 3, it's fine. So that's the kind of idea here, okay? So another one that I want to do, I'll just do one more, okay? Okay, I might do 2 more and then I'll leave it. So what about the limit as n goes to infinity of the square root of 4n squared plus 5 all over n plus 1. Now, this is kind of a trick question. So think about it before you answer. So again, pause the video and just try your best to figure out what the answer is. What's the highest power of n you see here? The answer is n. This n squared, it is n squared, so it is a higher power, but it's under a square root. So the square root of n squared is actually just n. So the highest power of n you see here is simply n, okay? So this, you would divide the top and the bottom by n. So you'd say 1 over n into the square root of 4n squared plus 5 all over 1 plus 1 over n. Okay? This is equal to the limit as n goes to infinity of 1 over n, that's the square root of 1 over n squared, times the square root of 4n squared plus 5 all over 1 plus 1 over n. So remember, we have the rule that if you have root a times root b, that's equal to root ab from our indices and logs chapter. So this now is the limit as n goes to infinity of the square root of 4 plus 5 over n squared all over 1 plus 1 over n. Now, if I apply the limit as n goes to infinity, this 1 over n, again, as n gets really big, this just basically becomes 0, and this also basically becomes 0. Okay, so again, if you do 5 over 100 squared, 5 over 1,000 squared, 5 over 1,000,000 squared, you'll find fairly fast that will just go to 0. So I'm just left with the square root of 4 over 1, that's 2 over 1, which is simply 2. Okay? And that's it. Nothing more. So the very last one, it says find Sn if Sn is equal to 1 plus 2 plus 3 plus 4 plus ... plus n. How do we figure this out? So first of all, what's a? A is the first number, which is 1. And again, this is arithmetic because you're adding 1 every time. Okay, so in this case, your common difference is 1. So what's Sn for a linear sequence? Sn is n over 2 into 2a plus n minus 1 times d. So this is equal to n over 2 into, it's going to be 2 plus n minus 1. So this will simplify down to n squared plus n over 2. Okay? And now what they ask you to do is they ask you to evaluate the limit as n goes to infinity of the square root of Sn over 3n squared. So let's do that. So the limit as n goes to infinity of the square root of Sn, which is n squared plus n over 2 all over 3n squared. So first of all, I'm going to multiply the top and the bottom by 2. just to get rid of that awkward fraction, okay? That's going to be n squared plus n over 6n squared. Now, what's the highest power you see underneath the square root? That's n squared. So I can divide the top and the bottom by n squared. So it's going to be 1 plus 1 over n. So n divided by n squared is, n divided by n is 1. 1 divided by n is then 1 over n. All divided by 6. And if I let the limit as n goes to infinity, this becomes 0. So I'm just left with 1 over the square root of 6. And that's it. Okay? So that's what limits are. All right? And then finally, before we finish up on this chapter, the last thing we want to look at is a geometric series that's infinite. So we saw that Sn is equal to a into 1 minus r to the n all over 1 minus r. What happens if I do S infinity, specifically for the magnitude of r being less than 1? And this is very important. Whenever you're doing an infinite series, this needs to be true, or else you'll just get infinity. So it's like if I add 1 plus 2 plus 3 plus 4 and keep going up to infinity, I'll just get infinity. If you're doing a geometric series and the magnitude of r is less than 1, then you will actually get something finite. You will approach a number and you won't be able to go over it. I'll display that in a second. Okay, but for now, if I take the limit, sorry, I don't know why I did an S. The limit as n goes to infinity of a into 1 minus r to the n all over 1 minus r. What do I get if the magnitude of r is less than 1? I'm just left with a over 1 minus r. Why? Because this will go to 0. You can probably imagine if r is equal to a half, then a half squared is 1 over 4. A half to the power of 10 is 1 over 1024. If you keep going on to like some really big numbers, it's basically just 0. So you end up with this for S infinity. So S infinity is just a over 1 minus r. Now you might have wondered why. So the linear sequence made sense. It was because it was called linear because your Tn was a line. The quadratic was called quadratic because your Tn was a quadratic. Why is geometric called geometric? This is the reason. If I do a half plus a quarter plus an eighth plus a 16th, and I did it on forever, and I want to know what is the value of this, you would say S infinity, friend, that's equal to a over 1 minus r. So a is equal to a half. 1 minus r. R is what you're multiplying by. I'm multiplying by a half every time. That's equal to a half over a half. So it's 1. So this is saying that if you do this forever, you will get 1. That doesn't... You have every right to question that. That's the one thing about maths. Like, you have every right to question and say, hold on, that doesn't make any sense. I'll show you now why it was called geometric. Let's say I have a square. Okay, I might make it a bit bigger actually. How many would I go down? Maybe 8. I think that's 8, yeah. Okay, this is an 8 by 8. So first of all, let's take a half of the box. So that's the first half, okay? Then if I take a quarter of the box, I can't believe I miscounted. Okay, I'm sorry guys, this is a little bit poor from me. It's 9 boxes tall instead of 8. That's my fault. But let's just say we take a quarter of it now. So the 4, that's the quarter. Now let's take an eighth. Now let's take a 16th. And you can probably imagine if we keep doing this, so a 32nd, a 64th, on and on, and just keep doing it and doing it and doing it and doing it, we will eventually have the whole box. Now, if you keep adding these together, on and on, will you ever actually get 1? No. But in the limit, you will get 1. So the limit basically says that as you keep going and going and going, you will eventually get so close to 1. You'll get 0.99, 0.9999, 0.99999, and as you keep adding stuff on, you will eventually just get 1. Okay? Now, there's one thing to note about this, is that it's quite weird that this works. Because you're adding an infinite number of things. So why are you adding an infinite number of things but only getting a finite amount of stuff? That's quite weird. Another analogy to this box thing is like saying, if I asked you to stand opposite a wall and said, okay, go halfway, and you go halfway. And I say, okay, go halfway again, and you go another halfway. And then I say, okay, go halfway again, and you keep going halfway, and you keep going like that. You will never reach that wall. But at some stage, you will get so close to it that you can just say, oh, I'm basically at the wall. But the thing is, you know you'll never pass out the wall, because I'm always saying, go halfway to the wall. So you'll never be able to get to the wall, and you'll never go past it. So that's why you can take an infinite number of steps towards the wall, but you'll never actually go to it. So long as you always only go halfway to the wall. Okay? So that's the basic idea of this. Okay. So I'm going to do one more question, which I think is a little bit hard, but that's just a geometry series. As long as the magnitude of r is less than 1, this always works. Okay? So something like -1/2 would work as well, completely fine. Okay, so the very last one that I want to have a look at is, how do you write something like this? As a fraction, in the form of P over Q. You do a geometric series. So first of all, you say this is equal to 2.9. So the 2 dots up here, sorry, I'm not sure if I've ever said it, but the 2 dots basically mean recurring. So that happens the whole time. So it's 2.9, 60, 60, 60, 60, 60. So that's what the 2 dots mean, that they just repeat each other. So this is equal to 2.9 plus 0.060 plus 0.00060 ... So now this is another geometric series, which is an infinite geometric series. So again, you'd say S infinity is equal to A over 1 minus R. So A is 0.060, R is 1 minus R, which is 1 over 100. I'm multiplying it by 1 over 100 every time. Why? Because my decimal places are moving 2 spaces every time. Okay? This is equal to, that's going to be 6 over 100, all over 99 over 100. So it's 6 over 99. And so P over Q, that's going to be 2.9 plus 6 over 99, which is equal to whatever it's equal to. So they could ask you to write this as a fraction, and this is how you would do it. You would look at, okay, what part is recurring? And then you say, okay, that's just an infinite geometric series. And then you plug it into your formula and then you'd solve. Okay? All right. I think that takes us up to the end of that chapter. So I think I'll leave that there for today. So thank you very much for tuning in, and I'll talk to you in the next one. Bye.